All right, welcome back. In this video for Professor Carbon, what we're going to do is talk about an electrophilic aromatic substitution mechanism, but it's going to have a little bit of a twist, and that twist is that there's going to be more than one product that's possible. And so I'm initially going to ask you to try to predict what those products are, and then we'll take some time to discuss them. The one hint I'll give in advance is for a Friedel-Crafts alkylation reaction such as this, over-alkylation is always a possibility. In this particular case, let's just clarify by assuming that we have excess benzene, and so that'll mean that we'll limit our product possibilities to those that have undergone monoalkylation. As with all these videos, what I encourage you, the viewer, to do is actually pause these videos, spend some time trying to solve this problem, and that'll really help out your ability to learn. Instead of just watching me talk through what the solution is, it's really important that you actually spend some time trying to come up with the solution all on your own. So please do pause the video right now. All right, welcome back. Hopefully you've had an opportunity to try to attempt these problems all on your own. And because it's an EAS mechanism, what I encourage folks to do is to follow my kind of simple two-step process here. So step one is always to make whatever our strong electrophile is. And then step two is to do the EAS mechanism. And that's true for almost all of our EAS mechanisms. And remember that there's really two steps to the EAS: attack and then loss of H+. So that's step two. And overall, that's true for a wide number of reactions. So here we have what look to be fairly simple Friedel-Crafts conditions. So aluminum trichloride is a great Lewis acid, and prenyl chloride is going to be a great electrophile. So let's just start the mechanism there. And remember, we always draw arrows from the flow of electrons attacking stuff. And that's significant here because often I see students take the Lewis acid and attack the electrophile. But that's backwards because the Lewis acid has a free orbital. And what we really need to do is draw the flow of electrons from the substrate to the Lewis acid. And this initial adduct always kind of makes me uncomfortable because, you know, I'm so used to chloride only having one bond that drawing it with two is really kind of strange to me. But nevertheless, this kind of Lewis acid, Lewis base adduct is going to be quite critical. And another thing that I find students often are confused with is formal charges on Lewis acids. And so here, if we're going to put, you know, an extra bond on chlorine, it has to be formally positive, and that means the aluminum has to be formally negative. As a reminder, that formal negative charge doesn't mean all the electron density is actually on aluminum. A good amount of that electron density will actually be spread around all the chlorine atoms and the Cl3 part. All right, now what we're going to do is break this off, and we're going to give chlorine the electrons, and that's then going to kick out AlCl4 minus as a good component. And if we're kicking off a negatively charged group, that means that we're going to have a cationic group. And the prenyl cation would be one of those. Now, some of you might be nervous because we now have a primary carbocation, and you may have been told not to draw primary carbocations. However, for those of you that have been through chapters on dienes or are experts at resonance, you might recognize that the prenyl cation actually has a resonance structure, such as this, where it's now tertiary. And so being allylic is much better than being primary, and being tertiary and allylic is just fine for a carbocation. So I think we can label this now our E. E+. So step one here was to make E+, and now we have a good E+. So now what we're going to do is our EAS mechanism. And so I'm just going to draw in my benzene. Remember, all of these are going to start by the attack of benzene onto that electrophile. And then what we're going to do is take those electrons, re-aromatize, and kick off our H+ leaving group here. Voila, So we've done our electrophilic aromatic substitution process overall. For those of you that are a little bit nervous with H plus coming off in the vacuum, just remember that typically we're not actually going to have H plus fall off. It will be pulled off by something, and the something that's most likely to pull it off is this aluminum trichloride. So overall, we'll take H plus our AlCl4 anion, and that'll generate then some HCl plus some more aluminum trichloride. So overall, that does balance out. So let's go ahead and put that one up here in the box. And normally I would say we're done, but unfortunately in this problem, we have this extra box B. And so we'll have to figure out what that can be. And if we go through our mechanism here, some of you may have already recognized this. If this carbocation is a potent electrophile, then this is actually another E plus substrate. So let's go ahead and draw an EAS mechanism from this carbocation as well. Just so we don't get our arrows mixed up, I'll use this one in red. So we have that attack here. And now we can do that exact same arrow here. And I'll point out that this is the attack, this is the attack step here. And that's the same step over here. And then this is the loss of H plus, and that's what we're going to do here. So loss of H plus. Ta-da! And so just fix that a little bit. And so that'll complete the other possible product over here. And so we could get two possibilities where that benzene can attack either half of the allylic cation. And so that leads to two possible products. Now, ideally, we could end up controlling which of these two products we ultimately form. And for those of you that have been through chapters such as adding, bromine to butadiene, you have the same issue where you can have a couple of different products. And sometimes we label these as being the kinetic product, that is the product that forms the fastest, or the thermodynamic product, the product where it ultimately forms the most stable product. And in this case, I would call this one the thermodynamic product. And the reason I would say that is it's because it has the more highly substituted alkene. So often in the chapter on butadiene or conjugation, we encourage students to look at forming the more substituted alkene as being the thermodynamic one. And that kind of tracks with most of the reactivity. Here, we only have a terminal alkene. And remember, the more substituents on an alkene, the more stable that alkene is. Or alternatively, the less energy you get out from a hydrogenation reaction with that alkene. All right, and so that would mean then that this would be the kinetic product. And that would kind of make sense because in our resonance structure, that's the one that we would consider to be the more stable carbocation. So that one should have the most or the majority of the carbocationic character in it. This one would have less carbocationic character, being primary instead of tertiary. And so that might make sense in that regard. So even though for this particular question, we're only asked to draw the products, we could take it a little bit step further and even try to label those products and imagine how they might form and under which conditions. Okay, so hopefully you've enjoyed this video, Professor Carbon. If you've been enjoying these videos, please do subscribe to the YouTube channel. We really do appreciate watching the number of subscribers tick up. It gives a little bit of encouragement to continue to make these videos, which hopefully are helping you understand and master organic chemistry. If you'd like the PDFs of these files, please do become a patron subscriber, and you can access them all on our Patreon page. Also, feel free to give us a like on your favorite social media account, Facebook or Twitter, and please tell a friend about these videos. Thank you.